That's a lot of video games. I didn't even know I had these. I want to play them all, but I don't know what order I want to play them in. So many possibilities. And that number can actually be calculated. So I have a stack of 11 video games right here, and I want to find out which one I want to play first. Well, how many possibilities is that? Well, there's 11 possibilities. One for each game. So which one would I want to play second? Well, that's 10 possibilities because we removed the video game that we played first. See, if you keep doing that for each number in order, you're eventually going to end up with one video game left. So how many possibilities in total is it to play all 11 video games? Well, it's 11 times 10 times 9 times 8 times all the way to 1. And this could actually be written as 11 factorial, or 11 with an exclamation point after it. In math, the exclamation point does not mean you shout the number out loud like 11! Although it is shocking how big these numbers can get. For example, 11 factorial is this number. Now say I only want to play 3 of these 11 video games. Well, it's not 11 factorial, but there's actually an equation you can get to find out how many possibilities there are. Well, the equation, I'll put it right there so I don't have to say it out. The equation involves multiple factorials and dividing these factorials. It's basically the factorial of how many total options there are divided by the factorial of how many options you didn't choose. And that number turns out to be this. So let's talk about the difference between permutations and combinations. Permutations are when the order of what you do matters, while combinations do not involve order. This can be useful when using Pascal's triangle. If you don't know what Pascal's triangle is, at the top there's the number 1, then there's 1, 1, then 1, 2, 1, then 1, 3, 3, 1, then 1, 4, 6, 4, 1, and it keeps going on forever. A good way to remember which number you're looking for is to look at the two numbers above it on the Pascal triangle, then add them up, and you got that number. For example, in the 5th row in the Pascal triangle, in the middle there's the number 6. Why 6, you might ask? Well, the two numbers above it are both 3's in the 4th row, so that's how you get 6. Pascal's triangle uses combinations, or possibilities in which order does not matter. So in the 5th row in the middle there's 6, you know that. But that is also 4 choose 2, which is 4 total options, and you choose 2 of them. The order does not matter. If it did, then the answer would be 12. So now that we know combinations and permutations and Pascal's triangle, we can find out the binomial theorem. The binomial theorem is this equation right here. If you have x plus y to the n, you can find out all of the coefficients to these using the Pascal triangle and combinations. Next, let's get to arithmetic sequences, or sequences of numbers that have a consistent number that you add to each number afterwards. For example, 2, 4, 6, 8, 10, 12, 14, 16, those all add 2 to the next number. In this case, 2 is actually d, or the difference factor, which can be used in this equation right here to find the nth term of an arithmetic sequence. Now say you want to find the sum of a number of terms in an arithmetic sequence, well, you actually can using this equation right here. This is a lot more efficient than just adding 2 plus 4 plus 6 plus 8 plus 10. It's a lot like multiplication as opposed to adding 2 plus 2 plus 2 plus 2 when you could just do 2 times 20. And it's a lot easier. Now we got geometric sequences, and the difference with geometric sequences is that they have a ratio instead of a difference. See, one number you multiply by a number to get the next number. For example, 3, 9, 27, 81, 243. The ratio is 3, and you can use that to get an nth term of a geometric sequence using this equation. Now if you want to find the sum of n terms in a geometric sequence, then the equation's a lot more complicated. I'll put it up there if you want to pause the video and copy it in your notes. There are actually multiple equations, one for which the sequence is finite and another for which the sequence is infinite, which is up there. Now you may be asking, Harper, What the heck does this have to do with real life? Well, arithmetic and geometric sequences play a huge role in determining compound interest, which is pretty important if you want to, make money. So for this next part, I was going to find an earthquake, but I don't really get earthquakes from where I'm from, so I'm just going to simulate an earthquake. This one's a magnitude 1. And this one's a magnitude 10! Ah! As you noticed, a magnitude 10 earthquake is a lot more than just 10 times a magnitude 1 earthquake. See, earthquakes work with a logarithmic equation, so a magnitude 2 earthquake would be 10 times magnitude 1 earthquake, magnitude 3 10 times magnitude 2, all the way up to magnitude 10, which is really, it's just unheard of. Now, how would you use logarithms in math? Well, if a to the power of x is b and you want to find x, just use logarithm base a of b and you got x. When using something like logarithm base a, b, base has to be positive and b also has to be positive. Otherwise, it just wouldn't work. However, there is one base that you're going to use for most of this math tutorial. Is it base 1? Nope. Is it base 10? Keep trying. It's actually base e, which is also known as the natural log. So that's why it's the most popular, because it's, well, natural. Now you may be thinking, but e's a letter! Well, in math it's actually a constant, and it's got some special properties that I'll talk about later in math. Finally, let's talk a bit about complex numbers. So, there's a bunch of real numbers, which is all the irrational and rational numbers. But then there's imaginary numbers, which has the symbol I, which is the square root of -1. Of course, they had to give a symbol to the square root of -1 because math has to be more complicated and, we can't have nice things. Then there's complex numbers, which is usually shown by the variable z. And it's equal to a real number plus a complex number. For example, 3 minus 2i is a complex number, so is 3 plus 2i. And you might be asking what happens if you multiply them together. Well, something really cool happens. If you know how to multiply polynomials, you've probably heard of the FOIL method. If you don't know how, then just look up FOIL method, and you're probably going to get something that has to do with math. So anyways, if you multiply the two complex numbers together, you get 9 plus 6i minus 6i plus 4. And how is that possible? Multiplying 2i by -2i, you get -4i squared, and I squared is -1. Multiply -4 by -1, you get 4. So that's how you get 4. And since positive 6i and negative 6i cancel each other out, you get the final answer of 9 plus 4, or 13. So if you multiply a complex number x plus yi with its conjugate x minus yi, you're going to get a real number, which is pretty cool. Complex numbers are a lot more interesting once you get into trigonometry and the unit circle, and we're probably going to get into that next episode. Foreshadowing next episode, we're going to talk about the unit circle. And it may look like a demon ritual, and you're probably right, because it's really, really complicated. This has been Harper Cates, and I will see you next time.
Which subject are we gonna teach next?
Spin the wheel to find out. Next time on Project E!